Okay, so Yongle Jiang, he's continuing his lectures on invariant von Neumann subalgebras in group von Neumann algebras. So,
thank you. Let's continue with the study of invariant von Neumann subalgebras. Let's recall that we mentioned for our talk, we will set G to be an infinite group, countable group. And we say G has some property, so invariant of algebra rigidity property. If average invariant from one subalgebra in LG is of the form average for some normal subgroup. And last time we mentioned that for now we have no several classes or examples with this property. So for example, we can have the following classes. Say if I take G to be a free group, or we can take finite many product of these groups. And we can essentially also take a cylindrically hyperbolic group, with trivial minimal radical. Let's denote by RADG to be the amenable radical of this group G, which is the largest normal amenable subgroup in G. And we can also take G to be, say, PS or Z for n no less than 3. This was proved by Callender and Panagonis. And if you look at all these examples, we see that all of them has trivial amenable radical. So in fact, a guiding conjecture is the following. So if G is a non-amenable group, then G has then radical G is trivial. Should imply G has the ISR property. This conjecture was not stated clearly in Keith and Doddson's paper, but they mentioned this. Okay, and there is a major advance in studying this conjecture, which was proved by Tatomasi, Yang, and Hanna. They proved the following wonderful theorem. I think it's 23. Yes, okay. The following thing holds. So let G be a countable discrete group. Let P be amenable G invariant von Neumann subalgebra. Then actually P is located in the group von Neumann subalgebra generated by the radical of G. So the only actual assumption is amenability here. So in particular, we can see that there is some direct corollaries to this theorem. So for example, if G is, okay, let's directly write if the radical is trivial. So in particular, okay, let's assume G is, say, non-trivial. And it's not the case we are trivial groups are not interested in. if this guy has trivial, this group G has trivial minimal radical, in particular it's non-minimal group with trivial minimal radical, then LG contains no cut-down subalgebras. Say A with an actual assumption. The normalizer of A contains G. So in other words, A is G invariant. This assumption means A is G invariant. The proof is similar to what we mentioned last time for checking this for free groups. You can apply this theorem. You can see this directly. Another thing is that this theorem actually tells you if you study this ISR property, you can always assume this invariant subalgebra is a subfactor. So let's just take a remark here. So if G has trivial minimal radical, and if P is a G invariant von Neumann subalgebra, then of course this relative commutant is also G invariant, which is clear from the definition of invariance. So you take the intersection, which is just the center of G, is also G invariant, and in particular it's abelian von Neumann subalgebra, so it's also amenable. So according to this theorem, by this theorem we know that this thing has to be trivial because the radical is trivial. So it's contained, the P is contained in the von Neumann subalgebra generated by the trivial group, which is C. So this means P is a subfactor. P is a subfactor. So whenever you deal with non-minimal groups with trivial or minimal radical, if you want to study whether it satisfies this ISR property or not, you can always start with an invariant subfactor. So for now, all these examples with ISR property come from non-minimal groups, and we also don't know actually how to write down a specific example to show this property is a property of a group instead of the property of this von Neumann algebra. In other words, we don't know, for now, we don't know whether LG, say, the question is, if you have two groups with isomorphic group von Neumann algebra, if this one group has this ISR property, does this imply H has the ISR property? By definition, this should not be true. But how to write down a concrete example? This was solved by me and Xiaoyan Zhou in December 2023. We showed that if you take G to be S infinity, this group has this ISR property. So recall that S infinity is the collection of all these bijections or permutations of this, say let's denote this guy by the collection of partially integers, such that the support is finite. So this means if you count how many points which is moved by this permutation G, this is infinite many, finite many. Sorry, this is moved by this. This is the support. This is the definition of support. So you can actually define it as the union of this Sn, where Sn means the bijections of n which only permute the first n many elements, 1, 2, 3 until n. It fixes any other elements. So of course it's a locally finite group, so it's amenable. Why this theorem tells you this Then this implication is wrong in general. Well, you can observe, according to the initial beginning result of von Neumann, we know that this is isomorphic to the hyperfinite to one vector. And according to the theorem of Alan Kong, we know that it is isomorphic to any ICC amenable groups, the von algebra generated by ICC amenable groups. So now we take a special one. We take this Riesz product group, so which is defined as this special semi-direct product. You just use Z to permute these indices here. However, however, it's quite clear that this guy doesn't have the SR property, and therefore SR property is not a property of the von Neumann algebra. The von Neumann algebra is a property of the group, although it's defined using von Neumann algebras. This doesn't have this SR property by the same reason as we mentioned to deal with this semi-direct product group here. So now we do similar thing. So if you have this special semi-direct product inside here, we can consider a special invariant von Neumann subalgebra which containing this subalgebra generated by this special copy here. And that I collect all the elements such that when you define its, when you consider its Fourier expansion, we need the coefficient to be symmetric in the following sense. So if you take the coefficient of V, it equals the coefficient for minus V, the addition group, it's upbinding group. This is the inverse of V. By similar reason, this P couldn't come from normal subgroups. So this is the reason for this property, this as a property is not a property of the von Neumann algebra. It's a property of the group. So how do we prove this? So recall that whenever we start with invariant von Neumann subalgebra, I denote E to be the conditional expectation which is trace preserving. And our goal is to show take any canonical unitary. So I identified G as UG in the group von Neumann algebra here. I want to show it equals either 0 or G. And this goes for any group element in this group. The first thing you need to note is that if H is a normal subgroup as infinity, then you have three choices. Either it's trivial, or the M-1, or it may be just the collection of all even permutations. So it's defined as the collection of all these even permutations. So you only have three normal subgroups. So our goal is to show if P is G invariant, which G is as infinity, then this P must be trivial, the ambient von Neumann algebra, or just the von Neumann algebra generated by A infinity. The first observation is quite simple. It's still just based on how do you control relative commutance of a von Neumann subalgebra. That is, for any G in S infinity, if you compute the support of this guy, it's already contains in all elements in S infinity such that the support of S, so this is a permutation of integers, net positive integers, this contains in the support of G. Since G lies in here, the support is always a finite set. So this support of EG is already a finite set. The proof is quite simple. So for any S in S infinity with support of S disjoint with support of G, then you see if you compute SEG as inverse as what we did last time, we can just move this conjugation inside this parenthesis. Now since they have disjoint support, they actually commute with each other, so you get EG. So this tells you this EG lies in the relative commutant of all these S with this actual assumption here. So with disjoint support. But now it's easy to show using the lemma we mentioned last time. This relative commutant is actually contained in L of all these elements, all the subgroups generated by these elements. So this EG has actually a finite support. And now let's try to compute. So we start with simple G in S infinity. So trivial wise is okay. We don't need to care about. Let's start with this transposition. So you swap 1 and 2. Keep other positive integers fixed. Then we know the support of EG is contained in. Now this support of G is actually just 1 and 2. So support of S is contained in 1 and 2. So we have actually only 2 choices for S. It's identity or just 1, 2. So we may write the Fourier expansion by lambda times E plus mu times 1, 2. If you take the trace on both sides, by trace preserving, this is 0. But now the trace for the right hand side is actually just lambda. So actually you deduce lambda equals 0. i.e., so this EG, or just E1, this transposition is actually just mu times 1, 2. Now you apply this E again, since this is idempotent, its projection, so you get the following. But now this is E1, 2, which is mu 1, 2, so mu equals mu squared. So mu is 1 or 0. So case 1, if this E of 1, 2 is 1, 2, which corresponds to mu equals 1, then this means 1, 2 lies in P. But now by conjugation, all this transposition lies in P, but these guys generate the whole group. So actually, S infinity lies in P, so this means P is the ambient from an algebra. Okay. It's the ambient one. So we may assume this E of 1, 2 equals 0. This is the transposition equals 0. Now we have to consider E of 1, 2, 3. Well, 1, 2, 3 has support 1, 2, 3, 3 points. So you need to consider all the permutation on these 3 points. You have at most 6 many elements inside in the support of this guy. It's kind of a little complicated, but you can still handle it. So you can still show this is either 0 or it's 1, 2, 3. You need to take some work, but you can still do it. At most 6 elements in the support. That's fine. So subcase 1 equals 1, 2, 3. So this lies in P. Now by conjugation, all 3 circles lie in P. For any 3 circles, I, J, K, no pairwise distinct. But these 3 circles generate this A infinity. So actually, this A infinity lies in P. So this is L S infinity. But 1, 2 certainly doesn't belong to P. It's not so hard to show. P has to be L infinity in this case. So the most difficult case is this 1, 2, 3 equals 0. Of course, we also assume this actual sampling here because we are in this case. So let's directly write equals 0. We have no other choices because if you believe what we are to prove is correct, then we have to show P equals L of E, which is C. The goal is to show P equals C. In other words, this is good to say we have to show ES equals 0 for any S non-trivial in the group. But if we go on like this, when we are actually end, we have been stuck for this for a long time because if you keep going to compute, say 1, 2, 3, 4, the number of support will be no bigger than say 4 factorial. It's very complicated. It's very complicated. We actually didn't really try to do this because it's too complicated. The miracle happens is that if we switch to the capital viewpoint, we already okay. We can conclude this directly. So the point is that you consider the following map defined by EG, G inverse. So you are taking the coefficient of EG in the coefficient of support, the coefficient of G in front of G in the Fourier expansion of EG. And notice that figure 1 takes 1 value, and this is conjugation invariance. You can check it easily using this P is conjugation invariant. More importantly, this is positive definite. In the sense that for any lambda, maybe C1, Cn, and for any n, this is C, for any n. And for any S1 until Sn, in S infinity, if you compute ij equals 1 from 1 to n, and Cij, phi Sij inverse, this is non-negative. This is essentially based on reduced to the fact that this conditional interpretation is UCP map, uniformly company bounded map, bounded positive map. So whenever you have such a map, you can call it. Some people call it the trace. Some people call it the character. Let me call it the character in this talk. Okay. Phi is the character in this talk. Okay. Just like invariant measures in dynamics, we know that invariant measures can be written as an integration of algebraic invariant measures. So characters can be written as an integration of so-called indecomposable characters. Okay, and I think Professor Becker will mention this in his lectures last week. Okay, so let's just give you a name here.
I didn't mention. I'm talking.
Okay, sure. That's be fine.
In 2 weeks.
Okay, in 2 weeks. Okay. So now the point is that I should mention that this observation is not new. Actually, in the very beginning, Alexei Burger in their paper, they already noticed this fact. They also think this should be useful to study this classifying invariance of algebra, but they somehow they missed this simple observation here. If you look at our original proof, our original proof actually used the very famous theorem of Thomas which classify all indecomposable characters on S infinity. So it's a very, very big theorem. What we observe from this theorem is that if you take any indecomposable characters on S infinity, if you look at the value at the 3 circle 1, 2, 3, it's always non-negative. And if it equals 0, then this character must be the simple one, .e, which takes value 1 at the identity element, 0 on other elements. So we use this simple observation to finish the proof. Later on, when in the joint work with Atom, we observed that actually we can use a very useful trick to bypass the use of this big theorem. So here's a trick, just the observation here. So the observation is very simple. So for any non-trivial element in S infinity, we can find infinite many Tn such that Tn as Tn inverse, Tm as Tm. Of course, this is simple because ICC, but the actual thing we need is that we can have the difference between these two elements is actually just a 3 circle. So it's IJK. It's a permutation and 3 elements. Why this will be true? Well, let's take a look at a simple example. For any non-trivial permutation here, you can write it as a product of disjoint circles. So for example, let's take an example here, maybe say 5, 6, 7, something like this. Then you only look at the last circle and last digit here. Of course, you can just move 7 to any element you want by doing some transposition. So you can find some Tn to keep all other elements in the support fixed. Let's move 7 to n, say by a conjugation of 7n. Now, what is the difference? Well, the difference is really just you compute this product, which is n65, 5, 6m. So let's compute it. So 5 is moved to 6, 6 is moved to 5, so 5 is fixed, 6 to m. M not equal to n. This should be for any m is equal to n. So m is moved to 5, I think. Yeah, 5, sorry. Let's continue. 6 is moved to 5, m is to 5, 5 to n. So actually you got 6 mn, which is 3 circle. Okay, now, by our assumption here, E takes the 0 value for these special 3 circle, but by conjugation invariance of P, you can see this actually implies for any 3 circle, you get 0. So in particular, if you plug in the definition of phi, it vanishes at any 3 circle. In particular, it vanishes on this circle. So the circle equals this part. And then a very, very useful trick, which was used in many works in studying characters. We know that this phi s must be vanishing. And this s is the arbitrary element here. This is a very, very useful trick. I think Professor Becker would mention this. Yeah. In particular, in Professor Becker's famous work in publishing invention, he classified in decomposable characters of PS or NZ. He used this trick a lot. Okay. So the trick, maybe let's say this trick. This trick is for any group, a countable discrete group, for any character, for any S in G, in particular for non-trivial ones, if there exists this data, Tn in G, and if many, such that you compute this the difference is 0 for any n not equal to m, then phi s equals 0. This gives what we want because if you look at the definition of phi, notice that if phi s equals 0, by trace preserving, you can put E in the parentheses and then move outside. By positivity of this E, it's actually just Coulomb square of this ES. So once it's equal to 0, then ES equals 0. So you can say ES equals 0. This finishes the proof. This finishes the proof. Yeah. This is the.
So what should be infinity is not the Tn's.
Yeah.
The conjugates.
That,
Tn as,
Tn as Tn inverse. Not equal to Tm as the Tm inverse. Let's say infinite many, such that this is one condition, this is another condition. Okay, for any n not equal to m. Okay. So this is the initial idea why maybe the study of as a probability is connected to characters, and actually it does, and we have more applications of this kind of argument here. So at least for now, we know as a property is not a property of the Von Neumann algebra; it's a property of the groups. And actually, you can also show that modify the proof. You can show this A infinity. It also has this as a property. This is a simple group. Later on in the joint work with Arta, we somehow generalize this, extend this proof to deal with all the approximately finite.
Sorry, it's not a property or neither of the measure equivalence class. I mean, because the groups you gave are measure equivalent. I mean,
Yeah.
So it's
Yes.
your examples. It's even stronger.
Yeah. So
Might be a property of I don't know. They are not quite isometric. Probably these two groups. I mean,
yeah.
probably not.
Okay. So later on, I think in October 2024, we extended to further classes, to wider classes. So we prove, I think, three things. At least three things. One is that for approximately finite, have SR property. This is defined as the full group of simple Bratton-Lee diagram. The proof is much more complicated compared with this one, but it does use some character argument. I will not mention the proof here. The second thing is we realize that, remember that we have a guiding conjecture. Trivial minimum radical should imply as a property. And what about the converse? It turns out that the converse fails. So we have found some G with SR, but the radical of G is non-trivial.
You get one. I mean,
Oh, okay, now let's see. Now yeah. Yeah, non-middle ones. And the third thing is that we found a sufficient condition for ISR property. The following thing holds. Say, let G be an ICC group, infinite ICC group. Yes, G has some property I will mention, extract property involving property of characters on G. Then every invariant subvector is of form LH for some H normal subgroup. So in particular, you use Amrutha-Hartmann and Vermeer's theorem. We know that if we further assume G is non-amenable with just say trivial minimal radical, then G has ISR. So what should be the property we want to measure here? Okay. It's actually based on digesting a lemma in Kifan-Sun's paper. So maybe let's try to figure out what property we should have. Okay, let me say let's fix G. So if you want, you can take it to be an infinite ICC group. But at least you can. I want to assume with trivial minimal radical. This is the most important assumption I need. So it's a non-minimal group with trivial minimal radical. And the following thing holds. This is due to Kifan-Das in the first paper on studying the Schwerer-Stormy conjecture, and also appeared again in Kifan-Das paper. The following holds. So let P. Okay, let G be a group with this assumption. T invariant subvector. Then we can find some normal subgroup, such that the following thing holds. So Ln as the von Neumann subalgebra is generated by P and is relative commutant inside Ln. This is the von Neumann algebra generated by these two copies. Moreover, for any I use n. Okay, for any H in n, you can find some unitary in P and also a unitary in the second copy here, such that this UH, this is what I wrote for H in general. So it's AH times BH. Okay, maybe let's take a break. I will continue the proof. 5 minutes or 10 minutes?
5 minutes.
Okay. Let's continue with the proof. The construction is n of n is as follows. You simply collect all the elements G with this factorization. But now I don't want to appear. I don't want n to appear, so I have to take LG. Because P is invariant It's not hard to see. This is a normal subgroup. The point is that you have to show P is contained in Ln. It's based on the following observation. So let's write it as a claim. For any G in G, if you compute EG star EG, it's actually commute with P. So check it for any A lies in P. Let's play a game. So I want to compute this guy and I want to get. Okay. So actually we know that this is just the EG inverse. So let's put it inside first. Now since A lies in P, so you can move inside GA. Now write it as conjugation of G and then times G. So this is GA inverse times G. Now once again P is invariant. A lies in P, so this lies in P. You can move outside. Once again, you put it inside. Now this is G inverse, GA, G inverse, cancel out, A, you move outside, you get what you want. Okay, because P lies in P. You can move outside this G. So it commutes with any element in P. But now, since E is a conditional expectation onto P, so actually this element also lies in P because two elements in P compute product P is an algebra, so it's closed. But P is a subvector, so this means the trivial center of something. So we may write EG star, EG. Say it's a scalar, let's write it as CG, which is positive, which is non-negative because it's the left-hand side is a positive element, positive operator. But now we see that, so if EG is non-zero, okay, then this guy is non-zero, so CG is non-zero, so it's positive. Then we can just divide both sides by root of by CG and split as the product of root of CG. You get 1. But now we are in the finite form algebra LG. So you can actually switch them because it's finite form algebra, you can play with the twist. We can actually switch these two guys. That means this is actually a unitary in P because this lies in P. So remember that we have this assumption here. And then I want to decompose G. So G equals G times 1. 1 you just write it like this way. Okay. It's an exercise to check this lies in TP prime. Since this is the unitary, because this is unitary, this is unitary, so this is unitary. So lies in the relative commutant. This is played. This can be proved using the same strategy here. So we see if we set AG equals this part, which lies in P. BG equals this piece. Then we see G lies in the subgroup N you defined. So in other words, we have proved that EG non-zero implies G lies in N. And now this actually implies P is contained in Ln. Because this is equal to say you want to check every element in P. You consider it support. I denote it by support P. which is a collection of all these support with element in P. This actually contains in groups elements G with EG non-zero. This is put in previous lecture because say G lies in the support of some element in P. By definition, this means power of xg inverse is non-zero. But now you use trace preserving. This equals to E of xg inverse. But x is in P, you can move outside. You see, this is non-zero, so this guy is non-zero. So in particular, this is also non-zero. But now, as what we showed here, it's lies in N. So once you know the support is contained in N, you know P is contained in Ln. Let's check this. Let's check this Ln equals P, the von algebra P of P, von algebra generally P and its relatively Ln. This is clear because we showed P lies in here. This already lies in Ln, so this is clear. For the other side, I use definition of N. So whenever you have element in N, you have this decomposition. But now we already showed P lies in N, so this lies in U of Ln. So in particular, you can start from here to see that this lies in N, this lies in N, so Bg actually lies in Ln. So here, Bg will actually lies in the relative commutant of P in Ln. So you see that for any H in N, UH is AH, BH. With this lies in the unitary group of P, with this part lies in unit group of this relative commutant in Ln. So you see they are equal. Now to continue the proof, remember that we want to deduce G has ISR, so we want to deduce P comes from a normal subgroup. The natural thing to do is you want to claim. So the goal is to show either this P is triple, the C. Of course, this is the triple element, the triple subgroup generated, the von algebra generated by the triple subgroup. Or you want to claim the relative commutant is C. Once this is C, then P equals Ln. And we are done. This is actually the difficulty they have to deal with in their papers. They don't have a general criterion when this should be true. But they can prove this holds true for various classes of groups, including a cylindrical hyperbolic groups with trivial member radical. But now the new thing we observe is that we can formulate a character condition to make this true. Here is let's erase the proof part. Here is an observation here. So once again, we introduce characters. I denoted by phi and psi. Oh, sorry, the characters. Psi defined in the following way. Let's denote. Okay, you have P, so it's a conditional repetition by E. It also has some relative commutant denoted by E prime. Okay, I define phi using E as before. I define psi using E prime as before. Those are characters. Now you observe P equals C. This is equivalent to say phi actually is the trivial character. So taking value 1 at the trivial element and 0 and other places. Now, another thing is that what is the case when this equals to C? This means if you consider psi restrict on Ln, restrict on n, this equals 30E. This equals 30E. So at least if this equals true, this tells us phi, say phi g psi g equals 0 for any, say, non-trivial element g in n. Does this hold true in general? Yes. So we can start with this decomposition here, really to compute it. So let's compute it. So remember that for any g, okay, maybe let's use h. Any h in n, we know let's switch to this h notation here for simplicity. Okay. It decomposes as this product. If you compute EH, this is lies in P, so move outside. Now notice that this E of BH actually lies in, first it lies in P because it's conditional repetition on P. Moreover, it lies in P prime because once you have an element in P, if you compute this, you can move inside. But remember, this element this lies in this P prime, so you can commute them. And then you move outside. Okay? So now it's lies in C. So actually, this implies E of BH equals trace, which is tau of BH. Then we can compute phi H, which is tau of, for definition, H inverse, plug in EH equals AH times tau BH. Now H inverse, you take the inverse, remember they commute with each other. If you want, you can use that fact. So now by trivial property, you cancel them out because they are unitaries. Now you can move outside because it's scalar. So it actually gives you this trace BH takes the module and take the square. So this is what we get for phi h. What is psi h? It's E prime H inverse. And now E prime H equals E prime AH BH. Now BH can be moved outside. I claim this also equals tau AH BH. Well, for this proof, it's not based on this calculation, but it's similar. To check this, you have to check, say, you can check H minus the desired answer here. You consider this as a projection, as H minus its projection onto this relative commutant, so you have to check for any element in Y. In this relative commutant, you get a trace 0. But now this boils down to this fact. Whenever you have any element in the relative commutant, you take the trace of E. It's a scalar. You can check this holds true. So with this calculation, you can see that psi h actually equals tau of AH squared. So now compute the product. You actually get tau of AH, tau of BH. Trace, take the product module and take the square. But now, since they commute, and also P the subfactor, this actually gives you a tensor product. Of course, you don't need this fact. You can directly use okay, let's maybe not write down. So this equals tau of AH BH because tau H BH is tau of trace, AH BH move outside, tau of AH E of BH. Now E BH can be computed with using tau BH. So you can actually split. But now this is tau of H. which is 0. Because H is a non-trivial element. For any H is non-trivial element. So actually, what we have from this fact is that if you define phi psi in this way, actually phi h psi h equals 0 for any non-trivial element in N, and we want to deduce phi delta E, maybe you can put a restriction here, or psi equals delta E. It's kind of a splitting property. Now we just write the property we need. But there's some subtlety here. We couldn't use N because N is a mysterious normal subgroup. Let's put just G here. And you can check, assume this implication holds for any phi psi characters on G. Then it automatically holds for any normal subgroup. If you replace this G by N and refer this to N, it also holds true because you can extend characters on normal subgroup trivially to the whole group. It automatically holds. And we call this property the non-factorizable regular character property. Okay. Okay, this is what we need. Once we have here, then we are done.
So maybe you should define the property.
Okay, let's see.
Characters and so on.
Yeah. Non-factorizable regular character property. Let's call this by this is so-called non-factorizable regular character property, I think. A regular character really just means the character delta E. So we can think of the same phi times psi pointwisely equals delta E. Then one of them equals delta E. This is not a well-known property for characters. We have groups with this property. So for example, let G be sometimes it's called character simple, sometimes it's called character rigid, and so this really means for any character you can find a scalar between 0 and 1 such that phi equals lambda, the constant function on G, plus 1 minus lambda, the constant function, the regular character, delta E. And this notion appears, for example, in Professor Becker's and Belhap's book. And for example, you can take G to be, I think it can be PR3Q for any n no less than 2. For n equals 2 is due to Kirillov, and n no less than 3 is due to, no, the other side, sorry.
The other side.
Yeah, the other side. For n equals 2 is due to Peterson-Tom. For n no less than 3 is due to Kirillov. Yes. Then G has let's take property star. Okay, it's too much words to write. Property star. The proof is quite simple. It's calculation. So take two characters. So y is here. Y is written using lambda. The other is using, say, lambda prime. So now if you start with this assumption, the product equals delta E. So this means, so phi s to psi s equals 0 for any non-trivial element s in G. But if you plug in as non-trivial element in here, this actually gives you what? It actually gives you lambda times lambda prime, because this is vanishing. This is vanishing. So one of them is 0. But now this actually says, this thing could say phi equals delta E, for psi equal to 3. There are more groups with this property. For example, you can take the group constructed in Austin's paper. So for example, you can also take G to be a non-amenable group with conjugacy classes who? Which means it has every non-trivial two elements in G are conjugate to each other. Such a group exists. Then it's not so hard to see every character can be written in this way, because the conjugation invariant property for characters. More interestingly, we can also take, say, G to be SL3Z. Then G has this property. I will not prove this. This is really based on Professor Becker's classification of indecomposable characters on SL3Z. You can do some similar argument. And actually, there are more groups. Lattice in higher rank, Lie groups. Some of them do have this property, but I will not say more about this. Okay. So this actually gives a new proof of Callender and Panagopoulos is the result that for SL3Z they have SR property.
So probability star is this one?
Yes. Really just non-factorizable regular character property. Yeah, it's too much worse, right? Too many. Yeah. And actually using this property we can prove this.
Do you have an example where you don't have this property? I mean,
yeah, this should be many groups without this property. For example, Z, integer groups. Because you can find two measures, property measures on Z, with the convolution to be the higher measure. But neither of them are higher measure on Z, such that. This really corresponds to the character defined by D. Yeah. This is the D.
I don't understand the hard measure on what. I mean.
Using this notion, you can.
The question was on which the hard measure.
On which?
Oh, okay. Huh?
Oh, you think the hard measure on the torus, on the side?
Yeah. On Z. Yeah, sorry.
Yeah.
This is the hash. So for this group, you can you can take A to be infinity times and H. H is a group here. These two conjugacy classes. Non-amenable group. So this is non-trivial minimal radical. You can do it. In the rest time, maybe let me comment that we have used this notion, and sometimes we don't need this precise property like this. In drama with my students, I think it's sometime here we can show that all invariant von Neumann subalgebras in SLZN for any n no less than 2 can be classified. I will not say the precise results for the classification, but let's point out that the starting point for this proof is that if you consider characters on Zn, if you start with these two characters, as I said, in general, for Z, it doesn't satisfy this property star. Of course, Zn doesn't satisfy this because this property passes to normal circles. However, if you put one extra assumption, so if you write it as integration of measures on on Tn. If you assume these two measures are SL and Z invariant, then these two measures must satisfy that one of them is higher measure. So in other words, if you start with two invariant characters on the n with actual assumption phi times psi equal delta E, then one of them is delta E. This is starting point for the classification. So this is going to say phi and psi SL and Z invariant. Yeah, so we use some kind of modified version, adding one actual assumption here. You can still deduce separate.
You don't use the, I use somehow, kind of, semi-direct product for SL3Z, I had to study such characters on SL2Z, SLNZ. Let's say, in this situation, I had to study characters.
Okay.
Probably at some point I had something like that.
I have still some minutes to. Let me briefly mention the study of this ISR property in the C-star setting. Well, I should mention. Let me say one more word. So in the joint with Tadomasi, Arthur, and Adamskowski, we study classification. We study the ISR property for amenable groups. We can get more examples of amenable groups with this ISR property. Moreover, we can show that there exists some amenable group with non-trivial abelian normal subgroups, but still has the ISR property. Yeah, because if you see for Z2 respect of Z, this guy doesn't have the ISR property because they have normal abelian non-trivial subgroups. So somehow this might be an obstruction to ISR property, but we show that this is not. Yeah. Let's continue with the C-star ISR. The definition is similar. So we say G has the C-star ISR property if any or every G invariant C-star subalgebra. This is always with uniform. Let's say uniform. In this reduced group C-star algebra is of the form for some normal subgroup in G. Of course, this notion can be defined easily, but we do have some examples. Before, I think. The example we have is the same as what we have for ISR properties. And I have a C-star ISR. Let's briefly mention the proof for F2. So first, we still start with a fact that P be a unital C-star subalgebra. Then P equals C-star reduced C-star of H for some H. If only if for any X in P and for any G in the support of X, where I think of X as an element in LG because this is contained in LG. So the support really means non-zero. Then we have to show G lies in with P. So for the converse, you just define H. For this part, you just define H to be element in P. Okay, it's really just UG. So now let's write G to be F2, generated by the AB. The goal is to show, say for P, G invariant, a unitary system algebra. The point is that we don't know how to show directly that exists some conditional expression onto P. So we have to find another way. Of course, the goal is to show for any x in P, for any G in the support of x, then P lies in P. This is the goal, or just UG lies in P. There is a miracle. That is lies in P for any primitive element in G. So for example, the primitive element means you couldn't write it as higher powers of other elements than G or G inverse. So A squared is not a primitive element. A is a primitive element. Yeah. Where is EG? Well, EG is denoted by the conditional interpretation onto the cyclic subgroup generated by G on this system of subalgebra. The point is that whenever you have a subgroup, you can have a canonical conditional interpretation onto this subgroup. So this is the tool we use to replace the conditional interpretation onto P. We use this conditional interpretation. The proof is by somehow you whenever you start with the element x in P, you can approximate EGX in norm by conjugation of x by GI, and then take the average. Okay. Let's assume this for true. But once you have this, then it's kind of exercise to finish the proof. So for example, let's take G to be A, for example. So X lies in P. So for convenience, I still use actually for the for the proofs I will write. It actually gives a new proof of Fn has the ISI property in the from algebra setting. So I will write this in the Fourier expansion version. But you can certainly use a finite approximation by group elements in CG to do this. Okay. So I will write this if-then sum. Okay. Okay. The CAN lies in C. X lies in P. The goal is to show. Say let's assume once again, let's assume this A lies in support of X. So this means the CA is non-zero. The goal becomes to show P lies in P. A lies in P. Okay. X lies in P. So it's kind of like in front of you, you have an infinite long string of sausages. You want a specific one. But how do you pull it out? You need some special knife. This is the knife we use. This knife is not good enough. Somehow, every time you cut it, you can have infinite many sausages. You don't get the specific one you use. Then you just rotate it to get the specific one you use. You need. Okay. It's kind of like a freeness argument. I will write down the details, but yeah, you just try it. You can find the proof. So here is the proof. So starting from here, it's not hard to see. If you compute conjugation of x by b, which is another generator of free group F2, and you consider the projection down to this cyclic subgroup of BAB inverse generated by BAB inverse, You get the same coefficient, but with different strings or sausages. Okay, this is another string of sausages. This also lies in P, because P is conjugation invariant, and also this property holds for any primitive element, and this is one primitive element. P is an algebra. You have to do product. BA, B inverse, and BA. You take the product of these two guys, compute the Fourier expression, A and B inverse. So you can use a knife. So you can use this special knife to cut this string of sausages. What do you get? You get only one, because you get only CA squared. A, B inverse. This is non-zero, and this lies in P, because this. So you deduce this B inverse lies in P. Now you have to somehow follow this pattern of proof to deduce A lies in P. So pick on. I think I would think of this as this you rotated. This is the group of A. This is group of B inverse. It's kind of like you put it in different position. You will get a unique intersection here. And now we want to show A lies in P. So repeat this argument, but using B squared instead of B. You will get a similar conclusion, but B is replaced by B squared minus. Now you compute it. A B squared A inverse B. This is A, I think, yes. Minus 1 B inverse is actually just B conjugation. In the middle you have B A inverse B inverse A lies in P. P is conjugation invariance, so B A inverse B inverse A lies in P. Now I can use this guy A B inverse B A inverse B inverse A to get A squared lies in P. We are so close. Then we do something similar. We compute Z defined as the element in P here, this element in P, and multiply by the conjugation of element in P. So it's still element in P. The product of two elements in P defined as Z, that's in P. So what's the Fourier expansion? B A square B inverse yes, and then we cut it using another knife. A B square A B A square B inverse Z. You get a unique term. A B A square B inverse lies in P. This is non-zero. We deduce A B A square B inverse lies in P. Okay, then we are done, because starting from here, we see you can use A B A square B inverse, A B inverse, which is A B conjugation. This guy is in P, this guy is in P, because we put here. We also put the beginning. You get a conjugation of A lies in P, so A lies in P. A lies in P. So something nonsense. Okay, it's based on calculations. But the crucial thing is we do have this. Inclusion here. Yeah, this is what you what do you prove to get this one? Yeah. Of course, you can modify the argument to deal with all elements G. If it is not primitive, you write it as a primitive element raised to some power and do something similar. Because you know in free groups you can have a conjugation of an element which is free from the given element. So it's kind of similar to what we did in previous talk. Yeah. But the point is we use a different conditional interpretation. One more word, that is, since this is a new notion, for now we only know these groups have C star S R, and we also know wherever a group has C star S R, it is either C star simple group or it's a very special amenable group, which is simple and with only only one non-trivial ideal in the four group C star algebra of this group. So in other words, we don't know whether we can show whether it's true or not. This guy implies the group is non-amenable or not. We don't know. Once we know this, this implies C star S, implies C star simple. So when I say C is amenable, non-amenable, this implies C is C star simple. So it's quite hopeful that all C star simple groups may have this C star S. Yeah. I will stop here. Thank you.
Thank you. Questions?
So especially you don't know it for A infinity. I mean, whether it has this.
Infinity don't have this. Doesn't have this. It doesn't have this C star S because the ideal, the non-trivial ideals is more than one. You have some non-trivial ideals besides the
structure of
kernel.
algebra.
This is not C star S.
So not. Okay.
This is not C star.
Other questions? I have a silly question. So now it's erased. You had the property star there.
Okay.
Yeah. It kind of reminds me, like, if you have some integral domain for the representation ring. I mean, that's stronger. But, that was a property for characters.
Okay.
Right. So is it related to something like that? Property star?
Maybe Professor Baker can answer.
I mean, you mean this non-factorizable?
Yeah, that it had like phi h.
Is delta? Is it?
Yes, yeah, phi h times psi
yes,
h.
is equal delta, then one of them has to
Yes.
be delta. You think whether it's?
That was only for characters, but.
You want to formulate this for what? For which?
No, I was wondering if it is related to integrality of a representation ring, of the representation ring. How?
Oh.
If it has to do anything with it.
So I think it's. It cannot be satisfied for character of finite dimensional representation. I think it's never the case, even for.
Yeah, I believe so. I believe so.
Sorry?
I believe so. It should be. Yeah.
It should be. Maybe yes. I mean, if you formulate this for general, I mean, representation on a field and so on. I mean, you can formulate something like that.
I have a related question, but maybe not only Tom Yongle. maybe to Bashir or other people from the audience. So in our paper we wrote that we do not know whether free groups have this non-factorizable regular.
Yeah. I should mention. Thank you for this question. So take any characters 5 psi, say I have f2 characters. Suppose we have the assumption in this non-factorizable character, regular character. We want to deduce phi equals to E or not. This is not known. But if the character comes from dynamics, so if you start with PMP actions, you define characters as the mirror of fixed point. This statement actually holds true as proved by Hanfeng. In that case, this really means if you start with 2 PMP actions of F2, if you consider diagonal action, if the diagonal action is essential free, one of them is essential free. This is known for special characters. Yeah. But in general, we don't know. Yeah, in fact, you can see that to check various groups have this ISR property, we don't have a unified approach. So if this true, this approach can unify the proof for F2 and SL3C.
That was actually the question also. I think there should be a counterexample for the free group. There should be an example, but
yeah, I should also mention that in Kakumasi, Yar, and Hana's theorem, the more important thing is that they introduced the notion of IRA, invariant random sum algebras, and Hana would present this in next week in her talk. It's a more promising concept, a new concept. Yeah.
Okay, so let's thank Yongle again. We go for coffee time.
Yes, also we.
It's always coffee.
Now the lecture is at 2:15.
What?
The lecture starts at 2:15. The second half of the. We don't have lecture.